Here's my two eigenvalues. One of them 5, the other one is 2. Let's just now try to find the eigenvectors associated with each of them. Lambda equal 5. For the lambda equal 5, is my matrix. Remember, for the eigenvalue, the associated eigenvector is the vector non-zero 1, which is a solution which is in the null space of the matrix like this. So here's my matrix. I just put 5 across this diagonal. Here's my matrix. Here it is. I need to find a non-zero solution and a non-zero vector which vanishes such a matrix. It's a row echelon form analysis, of course. So I fed this matrix into the computer algebra system. I took this to the row echelon form. That's what the computer algebra system gave me. Here's the row echelon form of my matrix. First row kept unchanged. Second one is 0, also kept unchanged. And the last one is just zeros. This is the result of the computer algebra system. And now I can find a non-zero solution. What do? I parameterize the non-leading column. I parameterize the unknown, which corresponds to the unknown leading column. Here's my parameterization. x3 equal t. I solve for the second unknown, x2, from the second row. It's the immediate solution. Here it is. And then I use that, and I solve for the last unknown, x1, from the first row. It's a back substitution we're doing right now. Here's my solution. Now if I combine this in a vector form, here's my vector form answer. Vector x should be a t multiple of the key vector like this. You can, of course, avoid dealing with the fractions here by introducing new parameters, say s, which is 1/25th of t, in which case your solution will take this form. And here's the vector which was supplied to us in my first slide. This is a vector which was supplied to us on my first slide. Now we found this vector in the pure analytical terms with no extra help from the outside. And my eigensubspace now, we can say, because eigensubspace, remember, it's a null space of this matrix, which is basically this solution, complete solution, and it is a span of this single vector. The spectral analysis fully completed for the value lambda equal 5. We still have another value. That's the one which brings us some uncertainty, because this vector, we saw this vector before. It's not a big surprise, we found it. But the second value, lambda equal 2, for that value, now I do the same analysis. Look at this. I build the matrix, A take 2, I. Here's a matrix. It's the same as this matrix, but now lambda is, I can move it. Here's my matrix. This is this matrix with lambda replaced with 2. Again, I use the benefit that I don't want to waste time right now on the tedious arithmetic, so I fed this to the computer algebra system, and the computer algebra system gave me the row echelon form of this matrix. Here it is. Again, we observe one non-leading column, which means that the null space we're going to find will be one-dimensional. It will be span of one vector, because we have only one non-leading column. So here's my analysis for the span. I'm going to parameterize the unknown, which correspond to the non-leading column. x3 I'll set to t. Then from the second line, I can solve for the second unknown, x2. Here's a solution. It's 1/2 of t. And then from the first line, I can solve for the x1. It will be 1/2 of x2, which is in turn 1/2 of t. So it's 1/4 of t. If I put this in a vector form, it will be a vector like this. If I put this in a vector form, again, if I just renormalize my parameter like this, it takes simpler form, 1, 2, 4, and here's my associated eigenvector. And the associated eigen subspace is 1, 2, 4.